from Bonn, who will speak about flatness implies smoothness for the porous medium equation.
Thank you. Well, first, I would like to thank the organizers for the invitation, for being here, and for giving this talk. I'm going to talk about regularity for the porous medium equation, and this is joint work. I mean, it's something which has been on my mind for a long time, but it is joint work now with a student, Clemens Kienzler, and Jean-Louis Vasquez. So we look at the porous medium equation, which I suppose that all of you have seen. Let's say in Rn, where m is a constant larger than 1. And I guess it's always good to look at special solutions to get an idea of what's going on. And the simplest solution is a traveling wave solution, which is xn plus t. Well, I guess if I write it this way, I have to take m divided by m minus 1 times t, the positive part of that, and 1 to the power m minus 1. So this is we're looking for weak solutions, and I don't want to be very specific about the type of solutions we look at. That's not so important for the porous medium equation, because basically all non-negative solutions, I didn't write that down, we look at non-negative solutions to the initial value problem. And basically all reasonable notions of solutions coincide. So weak solutions are the same as viscosity solutions, and there are many different things one could do. There is a very good theory about existence and uniqueness and so on, which I don't want to elaborate upon. So basically for any solution there is some initial data, and for any initial data in a reasonable class there is a solution. So this is pretty well understood, partly due to work by Koenig and co-authors more than 20 years ago. Now, this is a solution. If you take the positive part, so the support is a half plane, and it's moving in one direction. And this is sort of typical example. If you start with something which has compact support, then the solution at fixed time has compact support, and it is spreading all the time. So if this describes gas in a porous medium, if at a point there has been gas at a time, then it's going to be there at later times, and things are spreading. But if we start with something which with compact support, then the support remains compact. So this is a traveling wave solution, and it also gives an idea about the regularity. So if you take that to the power n minus 1, you get something which is Lipschitz continuous, and which is smooth up to the boundary of the support. And the velocity is related to the slope at this free boundary. So the boundary of the support is a free boundary, and that makes this fit to this program. Now, the main theorem is the following. So the assumption is, well, there are some constants. So let's say there exists delta larger than 0, so that the following is true. We look at a solution to the porous medium equation in a ball of radius 1 around 0 times, so now this for x minus 1, 0. And what we assume is that if you look at rho of x and t, then this is less or equal to a traveling wave solution, xn plus m divided by m minus 1t plus delta, positive part, 1 and minus 1, and it is sandwiched between two such traveling wave solutions. So this is the assumption, it's sandwiched between the two. And then the consequence is if you look at rho in a smaller ball and smaller time interval, then it is smooth on its support up to the boundary of the support. And what else? Rho to the m minus 1. In order for this to be true, we have to take the power m minus 1. And what we also know is that rho plus rho to the m minus 1 plus the m minus 1 is larger than, well, I guess if I put it this way, I may put 1/2 on the set. So this tells us that either, so this is in the support. The set where is larger than 0, intersected with this cylinder. So maybe I should. So this tells us that either we are in the set where rho is positive, or at the boundary of the support the gradient doesn't vanish. So there's a transversal intersection at the boundary. Now, before I come to the proof, any comments on the proof, let me tell you something about the context. So there have been a lot of similar results by, here is in smooth C infinity, but so let's say the pressure, this rho to the m minus 1 is called the pressure. Let's say it's of class C1 alpha here on the support, and suppose that the gradient doesn't vanish at the boundary of the support. Maybe even some stronger assumptions, it's not so essential. And then there is a stronger conclusion in a paper by Pavarelli, Vasquez, and Polanski, which says that then the velocity is always larger than 0. So the gas is spreading out, but the velocity, the normal velocity at a point, if this is satisfied, is never going to go to 0. So it's uniformly spreading out. And then in 1999, I showed that this implies smoothness. C infinity in the sense which I described here. So the question is, for example, what happens without this non-degeneracy, without this regularity non-degeneracy assumption? Could it happen that the velocity becomes 0 at a point? Could the gas stop spreading? Well, this argument here, then this theorem then implies that this can't happen for very large times, because then the solution is locally sandwiched between two traveling wave solutions by comparison arguments, and then the gas can't stop, no matter how bad the initial data. So this was one of the motivating problems. What I guess is sort of reasonable is a conjecture that much more should be true. So here we say that if the density of the gas is sandwiched between two traveling wave solutions in a cylinder, then it's going to be smooth. But one might hope for more regularity without this assumption. And what are the bad guys? Well, bad guys are if you have gas initially supported in a set like that, then it's going to spread. So let's say this is the initial support. Then it's going to spread. It's going to go out here, and it's going to fill the hole here. And at the point when it's filling the hole, the velocity becomes large, and the pressure, this rho to the m minus 1, is not going to be Lipschitz continuous due to special solutions by Carvalho, Ernst, and Carvalho. We have special solutions which show that the pressure rho to the n minus 1 is not Lipschitz. So if you want to get more regularity, then we have to have control on the geometry, because if the geometry changes, then things can't be smooth, and we have to get control of whole fields like that. So conjecture would be, suppose we have monotony in a cone of directions, of spatial directions. So locally we have a picture like here, where we have monotonicity in all these directions here. And suppose that we reach a point, so let's suppose that the gas reaches a point. And all this is local. Then I'm not aware of any obstacle to having smoothness in the sense described here. I have no idea how to prove that, but I guess that to me at least seems to be a reasonable projection. Now, let me come back to the theorem and to the proof of that. Well, this general strategy goes back to Caffarelli, and he has used it for many different things. This general strategy is, so suppose you have this flatness. That you have this flatness, so that the solution is sandwiched between two traveling wave solutions. Then, at the point 0, you may rescale and rotate, and if you're able to prove that with that you get an improvement of the flatness, then you can iterate the procedure. So the key is proposition, which says assume the assumptions of the theorem, then rescaling plus a rotation implies flatness, the delta over 2 flatness. So if things get flatter and flatter, then you can iterate that. That gives you C1 alpha control on the free boundary, if you look at what that is. And if you have C1 alpha control on the free boundary, then business to get a bound from below on the velocity, and with that closes the whole business. So this is sort of standard argument, at least to up to C1 alpha, and then we are in the regime where we already know things.
I'm sorry, maybe very simple question. Is rho larger or equal 0?
Yeah. Oh, sorry. I should write it like this. That's a perfect.
But then when you say smooth up to boundary, this means that
It means
we have like this quantity is larger than 1/2, and smooth.
The sum is larger.
the sum is larger.
Yes.
So near the free boundary, rho goes to 0, but it goes down.
Yeah.
But what is it that,
Okay.
I mean, what is it that, so rho to the m-1 is moved up to where?
Well, up to the boundary of the support. So there is, I mean, it is Lipschitz, it's 0 here, and it's going to hit this transversally, but up to that, it is going to be smooth.
So the boundary is well-defined gradient.
Yeah. And any derivative, any higher derivative. I'll take limits of any higher order derivative, and that's continuous. So what we have to prove is somehow far less. We have to prove the flatness. Now, where does this come from? And what is the context? This follows from a number of lemmata. So the first is, let me put a 1 in front of it, which has been the thesis of Clemens Kienzler. And this does the following about global solutions. So suppose you have some initial data, rho 0, This is the initial data. And what do I want? Well, I want that this is pretty close to what we have here. So if I look at rho 0 to the power m minus 1, and if I take the gradient of that with respect to x, obviously, because there's no t, and if I compare that to the unit normal vector, to the vertical unit normal vector, and if this is less than some mu, then the statement is, so there exists some mu, maybe I should say that there exists some mu larger than 0, so that if the gradient of the pressure is close to the vertical vector, so in the set larger than 0, so this is going to look like, so it tells us that it's going to look like the traveling wave solution with some, at least if you take the derivative.
Globally, right?
Globally. So this is globally. This is in n 0 infinity. Let's assume that it's not identically 0, then that would be trivial, but then there exists a smooth solution. And what do we know? Well, we know that there is a lot of control also on derivatives. So if we take dx to the alpha dt to the k at rho to the m minus 1 with respect to x, if we take the absolute value of that and if we multiply it by t to the alpha plus k, we have some other estimates, then this is less than a constant times the sup of this quantity. Well, here I should say minus en sup of minus en. So, well, what this says is, if initially we are close to the traveling wave in the sense of a derivative, then we're going to stay close to the, at least for the gradient, and there's some more statements, close to the gradient. And if we take the derivative, then we stay close to that in a smooth sense, where we have to take the natural weights which come from scaling.
What does it do? You take the derivative of constant?
Well, if alpha plus,
If you don't take any
if it's
derivative,
0,
you
if you don't take any derivative, then you're close. So in a smooth sense, close to the derivative, the gradient is close to en, to the vertical normal vector, in a smooth sense. And this also tells you that higher derivatives are going to decay. And all this is obviously in the set where so we larger than 0 and might take the closure or not if it continued. So I guess I have to say a bit more about this result. How does one prove this result? Well, let me give a sketch of the proof. Doing it completely would be too much. So this result is a bit unusual in the context of the porous medium equation, where one usually works with L1 contraction semigroups or similar things. And this works in a sort of smooth category. And I have to explain a bit about that. Now, if you look at the pressure being m to divided by m minus 1 times rho to the m minus 1, so this is the proper normalization or standard normalization, then this formally satisfies an equation pt is equal to m times p Laplace p plus grad p squared. Now, we search for a solution which looks like a traveling wave solution. It's a free boundary problem, so we don't know where the free boundary is. And this is usually a problem if you want to deal with smooth solutions. So what we have is a picture. Let's say here we have P. Here we have xn. And the traveling wave is moving like that. And we don't exactly have this, but what we know is that at least the derivative is always close to that. The function itself may be far away. Now, in this picture, it's easy to transform it to a problem with a fixed boundary. So if we exchange the role of xn and p, we simply rotate the coordinates, we rotate this picture, and then this picture is, well, this picture becomes, is it this? Well, I guess it is just like this. We exchange the coordinates, and our surface becomes, well, the graph becomes this. Describing the graph under this assumption here, and the assumption is exactly the same as prescribing the function. So we parameterize the graph either with respect to xn or with respect to p. Whatever we do, we're going to describe the same surface. If we describe it in this fashion, if you put xn be equal to xn here and p here.
I think the people in gas dynamics call this von Mises transformation.
Yeah, this is von Mises. Goes back to von Mises. It's a change of variables which reduces the problem to a problem on a fixed boundary. Before I write down the equation, let's just think a bit about it. Now here, in the positivity set, we have a parabolic equation, uniformly parabolic equation. Parabolic equation describes some sort of scaling, some sort of regularization, and it describes some regularization of the graph once we have control of the gradient. So we can be sure that we do get a parabolic equation in the transformed coordinates. Doing the calculation is messy, no question about that. But from abstract reasons, it's clear that there's going to be a parabolic problem here. Now, what is it? Well, let's call this yn. And if you look at the equation with respect to yn, then we get bt. So we're on the set where yn is larger than 0. And what is the equation? Well, the equation is minus, I want to write it more complicated than necessary, yn to some power, then we take the gradient with respect to rn minus 1, the first variables, yn to some power, which I'm going to write down in a minute, and then we have the gradient with respect to rn, so this is the divergence, v, so this is with respect to the tangential variables. And I guess I want to write it as a 1 plus sigma minus sigma, and sigma is larger than minus 1, and sigma is a function of m, which I could give explicitly. So this is with respect to the tangential variables. What happens to the other ones? Well, here we get a plus, and we obviously could put this in and get a power 1 here. So here we get a dn. 1 plus sigma times, now I need a bit more space, we get a 1 plus v squared divided by vn is equal to 0. dN is the derivative in the, maybe I should write it dNV. So it takes some algebraic calculations to see that this equation is perfectly parabolic. And in the case when we have, so if we linearize it, linearize around the traveling wave solution, then we get an equation Wt minus xn to the minus sigma 1 plus sigma greater than W is equal to 0. So this is an equation, I should put yn here. This is an equation that set yn larger than 0. We might prescribe initial data here. And it's sort of parabolic equation, and the remarkable property is that there are no boundary conditions at xn equal to 0. This is related to the degeneracy. And there should be no boundary condition because for this problem we don't have boundary conditions here. So the first job to do is to analyze this equation. So we have to think a bit about what that means and how that should be interpreted. Now let's forget about this sigma. Let's set sigma equal to 0, which corresponds to n equal to 2. And what we have is we have a weight xn in front of the Laplacian. If this would not be there, we would have a standard heat equation. If you would have xn squared, then that would be the heat equation on the Poincare half plane. So we have something which interpolates between the Poincare and the Euclidean case. And this is a type of equation which is not in this form, but which is closely related to other things which have been studied quite a lot. It's something like it's close to squares of vector fields and degenerate parabolic equations, squares of vector fields, and so on. And in certain cases, it can be reduced to them. Now, what we know from there is that we should look at the geometry which is behind it. Whenever we have a second-order equation, then this defines a metric. This defines a Riemannian metric by signating the dual. So the coefficients define a quadratic form on the cotangent bundle. On the tangent bundle, we have to take the inverse of it. So we get a metric. And what does the metric do? Well, if you look at the length of a vector v at a point x, then this is going to be, v is bad. Anyhow, let me use xn to the minus 1. We take the square times the Euclidean length squared. So things distances get larger as we approach the boundary, but and they get closer together if we are far away. Now once we have that, we can try to play the equation and do what we would do for a heat equation or for parabolic equation with measurable coefficients or whatsoever. And we could try.
In your lines linearized equation, the gradient is the global gradient also.
Yeah.
Also in the variable xn.
Yeah.
Okay.
Yeah, the gradient is global. It's m variable gradient.
Yeah.
Yeah.
Okay.
So here I did denote this.
No, yeah.
So
The coefficient is only on the last variable.
Mm-hmm.
So there are
Let me ask you this question. So with this new metric, you are not saying that the operator is the Laplace-Beltrami operator in that metric?
no.
No,
That's
it's
it.
no.
You're not.
Well, is it the Laplace
You do as
Beltrami?
much as possible, but it's not the Laplace-Beltrami operator.
Is it the Laplace Beltrami operator? I mean, it's the Laplace Beltrami operator up to lower order terms, and lower order terms are of the type which come from this yn to the sigma. So it is.
Okay.
I would have to say more about it. There's more structure behind it, which makes
That
it
is.
natural to look at a one parameter family and not at a single operator here. Even though I have to say I don't quite understand that, and when I try to talk to people who should know, who I think should know more about it, then I'm always a bit confused.
Yeah.
So that, I mean, it's in this structure has a structure of a solvable group, and I don't know much about heat equations on solvable groups. Anyhow, so once you recognize that, then it's sort of natural to get heat kernel estimates. We might start with energy estimates. Energy estimates, heat kernel estimates. There are generalizations of Sobolev inequalities and all the toolboxes which we have for dealing with parabolic equations. And then with that we get kernels, and the whole Calderon-Zygmunt theory works. The whole Calderon-Zygmunt theory can be generalized that it's a space of homogeneous types, so all this works. So this is half of what you have to do. So this gives control of this equation, allows to deal with a nonlinear equation, but we want to deal with the nonlinear equation under the assumption that we have control on the gradient with respect to x. And this gradient enters the equation in a nonlinear fashion. So having pointwise control on the gradient is essential for getting anywhere here. On the other hand, it can't be obtained by the maximum principle or similar things. And then you would get with the maximum principle, if it were possible to use the maximum principle here, which is possible for the tangential directions but not for the vertical directions, then you wouldn't get, typically you wouldn't get as strong estimates as these here with the derivatives. So we have, for the linearized equation, the full toolbox we have usually for elliptic or parabolic equations. And we can generalize all these things, but still we are on a borderline case in terms of regularity, and we would be in a borderline case even if we would be uniformly parabolic, or if you would look at a similar elliptic equation or so on. So here the whole issue is not so much the degeneracy, but it is sort of a different technique. Now, this is where something else comes in. In the first place, I'm aware of that ideas like what he used appeared is in joint work with Daniel Tataru on the Navier-Stokes equations. Instead of looking at the Navier-Stokes equations, we could look at the harmonic heat flow, and there's some work by Van Holin and Wang, and also by Tobias Lamm and myself. One could look at the Ricci flow and similar things. There was always the same structure, but let's see, for the harmonic heat flow, what we do here would correspond to look at initial data in BMO. In this case, BMO with a small norm, with some locally small norm. And there is some techniques, and I don't want to go into that. What comes here is connected to Carlson measures. And with Carlson measures, this may be an interpretation which has not been here in the paper with Daniel Tataru. It became sort of clear in my work, more recent work with Tobias Lamm. So there is a relation to Carlson measures, and if you interpret that in a nonlinear context, then this is going to give you this result, and that is what Clemens-Kienzler worked out for the closed medium equation. So, what did we learn here? Well, what we learned is that if you want to, that we can do transformation of the problem to a fixed domain, and we can linearize that. The effect of that is that this linearizes the geometry and the pressure and the density at the same time. So this linearization here, this equation plays the same role for the porous medium equation as does the Laplacian for any second order nonlinear elliptic equation. So it gives the linearization at a point and gives a lot of information about the nonlinear problem. So if you want to get understanding of higher derivatives, more regularity of the porous medium equation, we have to look at the linearization and try to reach a nonlinear setting. So this is the first part.
Just a question about this one transformation. Do you assume that it's a graph in that direction? Or
Yeah. Well, I assume that for the initial data. And then I'm able to, if you're able to prove that that is a solution in that class, then we can go back. Now, how are we going to approach the improvement of flatness? So what we have is a space-time cylinder. We are looking at T, X, and then a space-time cylinder. And we want improvement of flatness in a smaller cylinder here. How could we get that? Well, there are a few observations. We are looking at the equation for the pressure. Let me write it down here. And let's say if P is larger than some capital lambda, which is much larger than the delta, the flatness parameter, which we had here, which would not be so important here, but it's going to be important later on. In this setting, in this set, this equation is uniformly parabolic. If you have a uniformly parabolic equation, then we know that we get control of derivatives. So here it's uniformly parabolic in the standard sense. And this implies that there are good estimates, but they are degenerate as P tends to 0. The pressure tends to 0 because there is degenerate. But if you stay away, you get good estimates of the gradient and all these things. So we know that we are close to the vertical derivative. If you look at the equation for the gradient of the pressure, then we can improve the regularity and get good bounds for that. But only in a set where P is larger than a constant. So what we do is we want to construct comparison solutions. And this is where we deviate considerably from the strategy of Caffarelli, I guess. So we fix some time T0 less than 0. And here we want to describe global initial data of some, we want to describe some initial data, let's say rho plus minus at this point T0. So that, this should be defined on Rn. And this should be so that we can apply lemma 1 to them. We want to be able to apply lemma 1. And we also want that rho minus should be less than rho plus on, let's say, B1 of 0 times T0, 0. But this is what we want to have. If we want to apply lemma 1, then we can do that by setting, so the idea is we set rho plus minus equal to rho, let's say for x less than 1/2, and for p larger than lambda. So this is a reasonably large set, let's say T0, and let me put the T0 here for the evaluation. Then we want to could rho plus, let me simply say rho plus T0 equal to, let me put the power m minus 1. It's sort of easier to think in terms of the power m minus 1. So here we want to look at xn plus t plus, let's say, 3 delta. And here we take the positive part. And here we want to have that for x larger or equal to 1. There should be T0 here, obviously. So we want that the positive part is certainly above this rho, which is bounded by the same quantity, this delta. We want to be above that. And similarly with the minus, which I guess I don't have to write down here. Now this leaves us with another set. Here we have xn. Let's say here we have this level. Then here we have this, basically this lambda. And if you are here, this ball of radius 1. And on this set, we have that rho plus minus is equal to rho. Here we have that it's much larger. And here we have little control on the gradient of rho, so we have to stay away from rho. So here we want to take, let's say, 2 lambda, and here we want to take rho plus equal to xn plus t0 plus delta plus for x less than 1. I could take 3 delta here, but that doesn't really matter. Let's say less than 3/4 to be here more precise. And if p is less than lambda. And in the areas between, so here we get this part here, in the areas in between, we do some sort of interpolation. So if we do that, what do we get? Well, we get, if we do it carefully, that the lemma 1 is applicable, so we would get global solutions. Then, by construction, we know that the initial data here, on this part, is outside, is far above rho itself, for rho plus. So this is going to stay like that for a while. So then we get a comparison principle. We can apply a comparison of the 2 solutions, and we get that on the parabolic boundary, this rho, so solution rho plus, I should put T0, the solution, corresponding solution rho plus is above rho, and is above rho minus. So we get with that this holds on the whole ball. So, now what else do we have? Now we have these guys, and we want to see that rho plus and rho minus is close to another on a set of that type. So we want to say that for some later time, if you look at some later time, which we have to choose properly, we want to see that rho plus minus rho minus, and I guess I should put the power, m minus 1, rho plus to the power m minus 1, minus rho minus to the power m minus 1. We want to say that this is small compared to delta, much delta 1/2, in a set where x, let's say, is less or equal to 1/4 for some later time. So why should that be? So we are interested in a smaller ball here, and we know that the initial data coincides on this part here. If you look at the difference, it satisfies a parabolic equation of the type we studied. So there are Gaussian estimates for the kernel. So we can express this difference in terms of Gaussian integral, sort of generalized Gaussian integral with respect to the initial difference. Now, as long as the time difference is small, we don't see the effect which comes from here. Now what happens here? Well, we have a Gaussian kernel, and if we choose a time where the corresponding distance in space looks like that, then we're going to average over this part here, where the distance is of size delta, and this here, where the both initial data are the same. So what we get is we get an average of this, or we get an integral over that divided by the volume of this larger ball. And if the difference of the volume of this part and this ball is going to be small, then we're going to gain here a factor in terms of delta so that this is closer together. Now, next, we use this theorem of Clemens-Kienzler. So the theorem of Clemens-Kienzler tells us that this function rho plus minus becomes smooth, so we have higher derivatives. Now, if we turn them around, because they are smooth, then the tangent space on the graph is close to the graph of them for a certain area. And if you put all of them together, then we get the improvement of the flatness and with respect to those tangent spaces. So the crucial part is the control of the higher derivatives and the heat kernel estimate applied to this setting. So, I mean, working that out and putting all the constants probably is a certain effort. So this is done. We are in the process of completing that. But I hope that I could present the idea and give some impression how this works. I guess the ideas are not so specific to this problem. What is sort of specific is that we have this degenerate parabolic equation where we know less than about the heat equation or harmonic functions. Yeah, so I guess that's all. Thank you.
Thank you very much.
I vaguely remember something in Kursa by Tortidas Kavo
Yeah.
and Richard Hahn. Is
Yeah.
it connected?
Yeah, so I guess I should have mentioned that in that area when I talk about that. So what they started with, and that was the thesis of Tortidas Kalopoulos, she looked at smooth solutions to the porous medium equation in the same sense as I did, but for smooth initial data. So this was simultaneously when I did my work for the habilitation thesis, which was then this. And then they worked, she and Hamilton worked quite a bit on the porous medium equation and used this.
Yeah, because there is this transformation, this kind of Legendre type transformation for this equation.
I wouldn't call it Legendre type because it's.
Well, I mean, it's not Legendre. I mean,
it's von Mises because it concerns. I mean, it concerns the graph of the function, and it's not connected to convexity.
Mm-hmm.
So.
But didn't they have something like this, like a metric associated with?
Sure,
Yeah.
sure. I mean, if you look for smooth solutions, you have to have that metric, and we came to that.
You just have a vague recollection.
Yeah, sure.
The next talk at the 15 minutes.